Okay, so you have my screen over there. Let me put this to presentation. Uh, this is not working. Okay, now it will work. Okay, so we are in business here. Let me see 1 second. Okay, just a sec. Give me a second since I am recording with the Zoom, which is a better quality. Let me just put this in presentation mode so it takes less memory. Okay, go. Oops, how did it go back? Okay. So hopefully this thing is gonna help me here. Okay, so now let me see a show of hands of who has seen the self-study videos and the podcasts and all the stuff that I put for your modules to complete the self-study videos. Okay, who has no idea what I'm talking about? Okay, who is awake? All right, so people are awake. Okay, so now we gotta vote for the other ones. Who has seen the self-study videos? A few people, all right. So you guys know that it is there, I hope. Okay, so just in case, let me show you here. Let me show you your canvas. Is it showing there? Yes, okay. So here, when you go to your canvas, we are now on week 3, right? Of course, we did not have class on Monday. That was Labor Day. Now here, when you go here to week 2, you will see that you have, extra Jove videos, and you have this video here. You have this file for self-study, okay? And make sure that you watch that because this is basically an inverted class, so we can catch up and definitely, make sure we cover what we're supposed to, okay? Besides all that, I added those new podcasts, right? So like bite-size videos that you can easily follow, right? So make sure you cover all that because you'll be responsible for that. It is going to be on your test next Wednesday, okay? So here we come to the part that we're covering now. And of course, I will add the video link. So everything that we cover now and everything that we get to cover on Monday is going to be on your exam on Wednesday. Okay? So make sure that you go over these topics. And also, I know that Bill has put up a study guide, right, for you to use as well. All right, so here we come to this lecture 5, that we're going to get to protein structure, basically, not much to function, but we are going to get to a protein structure. How do I do this with my pointer? Okay, so I'll try to do that. All right, so here, first thing, I want to make sure that everyone catches the most important parts on your self-study. So I'll fly through some slides just to make sure that you absolutely understand the points that you have to focus on. Okay, so let's pay attention. And the next slide is already going to be iClicker point. Okay, so make sure you get your iClicker app, so your iClicker ready to go, because next one is already iClicker point. Main topics of the self-study. You are going to focus on what is entropy, okay? Entropy and disorder. So you have to be familiar with the laws of thermodynamics, especially the first law and the second law, right? So the first law says that you cannot create energy and you cannot destroy energy. You can just make it change forms. So this first law of thermodynamics. The second law is the massive, the law of disorder. That is the entropy law. Or let me see, show of hands, who took chemistry, basic chemistry in the class? So everybody did. So this is just a brief brush through review. If you do not take chemistry, well, I think it's a prerequisite. So if you do not remember these things, make sure you go over them. Refresh your memory, okay? So law of disorder, it says that everything has a tendency to get messy, right? Things have natural tendency to become more disorganized. And the example given was this nice and neat room that with time, it naturally becomes messier. All right. So first and second law of thermodynamics. So here comes your first iClicker question. Okay, how is the entropy of the universe changing with time? So here you're going to have your choices, and let's make sure that you have your iClicker open. You got it there, Belle?
Yeah, we got it.
All right, so make sure you get your points here. Okay, so your choices are, how is the entropy changing? It decreases, it increases, it remains the same. What is entropy? Don't give me D.
Okay, the 30 seconds are up.
All right, so what is your answer here? Okay, how many people go for A? No, how many people for B? You gotta vote, people. I guess your arms. Yeah, your answer is B. It is going to increase. The mass is going to increase. Next slide is another question. Here it is. If a substance is changing from gas to liquid, what happens to the entropy? Now you have to think about what's going on with the atoms in that substance. It's changing from gas to liquid. Okay, you got the answers in?
Okay, it's been 30 seconds.
Right, I see most people answer A, and that is your correct answer. Your entropy decreases because the atoms in the substance get more organized. Okay. So here comes with the idea of Gibbs free energy, right? So what is this? It's the amount of energy that is available to actually get something done, right? And energy available to do work. And there is a relationship between the free energy and the enthalpy and the entropy factors. So you need to understand the relationship. Okay, so what happens here? Mainly in biological systems, we're going to have chemical reactions in which you're going to go from reactants to products, right? And some reactions are favorable and some reactions are not favorable on their own, right? So we see that if the reaction is favorable, it's going to be exergonic. If the reaction is not favorable, is mainly endergonic. That means you have to put energy into that reaction for it to happen. Okay? When you look in biological systems, you're going to have mainly the exergonic reactions that liberate energy are the reactions involved in breaking down substances. Okay, so exergonic reactions are mainly going to be your catabolic reactions when you're breaking down molecules that are storing energy. So you get a bigger one and you make smaller ones. So that is your catabolic reaction that also goes side by side with releasing heat energy. Right. When you have to put energy in to make a substance, to make a molecule, you're mainly going anabolic reactions. So those are not really spontaneous. Okay, they are not favorable. You have to put energy in and you have to do several tricks in order for those reactions to happen. So here comes again the idea of Gibbs free energy. When we look at what is it in the molecules that are holding potential energy, you're always going to be looking at the enthalpy factor, because this enthalpy is the energy that is kept in the bonds of the molecule. Okay, so covalent bonds are going to hold the energy, and that is going to be part of the enthalpy of the system. Okay. The entropy of the system is really going to tell you how messy it is, right? So that's the messy factor. Now, when you look here at the relationship with the free energy, okay, with the Gibbs free energy, you're going to see that if you have liberation of heat, basically, then your reaction is going to be spontaneous. If you have to put energy into it, then it's not spontaneous. So basically, if you have a spontaneous reaction, you are going to look for a negative delta G, so negative Gibbs free energy for spontaneous reaction. Now, if you have a value in your enthalpy that is quite high, and you take out another value that is not as high as your enthalpy, that means your Gibbs free energy would be positive. That means the reaction would not be spontaneous. So one trick that warm-blooded creatures do is to always have this temperature a bit higher in order to increase this factor. Okay, so if you're increasing a factor that is going to be subtracted from your enthalpy value, that might just push your reaction into favoring characteristics. Okay, it might be pushed into a spontaneous type of reaction. So warm-blooded creatures can increase that factor in order to make reactions more likely to occur or more spontaneous, right? So yes, in these very few first slides, there are lots of concepts that you absolutely have to be familiar with, okay? So here, temperature is going to amplify the entropy, and that might push your reaction towards a favorite bucket, okay? Okay, is everybody clear so far? Okay, so I'll assume yes. Now, this slide here also has a lot of information, okay? What is it that you have to look at here? Basically, not all covalent bonds are the same. There are some bonds that hold more energy, some bonds that hold less energy, okay? So you have to figure out which bond has more energy and which bond has less energy. In order to figure that out, you have to look at the electronegativity of the atoms that are participating in the bond. okay? So what does that mean? Look at the periodic table. When you go from alkalines to noble gases, okay, so moving towards the right, your electronegativity increases. If you go from the bottom to top, so towards the right and towards the top in your periodic table, your electronegativity increases. So the atoms that are more electronegative will want to hold on to those electrons. Okay, they want to hold on to electrons in the bond of electrons that they are sharing. Okay, meaning sharing electrons, that's what makes the covalent bond. So let's see in case here in the examples that we are giving with these molecules here. I wish I could know how to make this just a pointer. Oh, okay. Oh, laser. I just figured that one out. Okay. So let's look here in the examples given by these molecules here. If you look at the top molecule here of methane, we know methane is a gas, right? And it's combustible. That means if you ignite it, it will give off energy. It will burn, okay? So what happens here? You look at the carbon and you compare the carbon atom with a hydrogen atom, and you say, well, hydrogen wants to donate its electron. Carbon wants to pick up 4 electrons because it has 4 spaces and at the valence shell, right? So when carbon makes 4 covalent bonds, it is going to hog on to those electrons, and it's going to make the sharing of those electrons quite unstable. So each one of these covalent bonds is quite unstable. If you ignite it, you are going to get energy out of those bonds. Okay, you're going to get a flame. Okay, you're going to get energy out of that bond. Now, when you compare methane with another gas here, or this one is more of a liquid because it forms hydrogen bonds, right? So if you get methane compared to methanol, okay, alcohol, methanol, you see that the sharing of those electrons is not quite the same as with methane. All right, so methane is a lot more combustible than methanol. Because you look here at the electron clouds, so now you see that the carbon is not holding on to those electrons as much. Well, basically because it has to share a bit more with that OH group, okay, with the hydroxide group over there. So the bonds between carbon and hydrogen, although is the same type of covalent bond as you find here, carbon and hydrogen, methane, this bond has less energy than that bond over there. Okay? So what happens here is that you are going to increase the oxidative state of that carbon. Okay? That means the less the carbon holds on to the electrons, the more oxidized the carbon becomes. Okay? If the atom is holding on to electrons, it becomes more reduced because, of course, electron has a negative charge. Okay? So if your atom gets more and more to hold on to the electrons, that means your molecule is more and more reduced. Okay, so of course, oxidation and reduction have to go together because if one gains electrons, then something else has to lose electrons. You're not just going to make electrons out of nowhere. Okay? So know this comparison, know this principle here that as you get more oxidized, the molecule becomes more and more stable, right? So you look at the example here of carbon dioxide, the bonds between carbon and oxygen, well, first of all, this is a very linear molecule, right? So it's very organized and very much stable. But these bonds here are very stable bonds. That means they are not going to release energy as easily as a bond that would be, for example, up here in methane. Okay, I mean, you try to burn carbon dioxide, you're not going to be successful because that's a byproduct of a burned reaction. Okay, so that's the final oxidized molecule out of a reaction, right? So understand what is happening here with electronegativity and with the strength of those covalent bonds, right? The more reduced the molecule, the more unstable those bonds are, and the more energy this molecule can give. So a lot of concepts in this one slide. Okay, let's rush through here. Okay, so definition of oxidation and reduction. When you reduce something, you give electrons to it. When you oxidize something, you are losing the electrons. So hopefully that's not news. All right. Electrons, something that sometimes escape our minds when we are first studying chemistry, right? So electrons, they are a unit of energy, okay? And they all have a negative charge. But the electrons, not all the electrons have the same amount of energy, okay? One electron might be more energetic than another electron, but the charge that each one of them has, that is the same, okay? One electron has a negative charge, end of story, okay? That's the same for all the electrons. So here we get to the idea of bioenergetics. So what is happening inside of the cells? How is it that the cells manage to make reactions that are seemingly not favorable? How is it that the cell will push the reaction to happen, to become favorable, right? So this is when you come to this idea that you're only concerned at the overall picture of what is happening to the reactions. You want to know what happens at the beginning and what happens at the end. Then everything else that happens in the middle, you can justify that everything in the middle is coupled in order to allow a certain path to occur. Okay. So the bioenergetics here is going to predict whether something is going to happen or not, but then at the same time is not really telling you how long the process will take. Okay, let's say you have a favorable reaction. If it takes 100 years, well, we are doomed because even our lifespan it doesn't get to be 100 years usually, right? So is the reaction favorable? Yes, but it takes forever. So, well, that's not useful. Although it's favorable, it might not be useful. So whether the reaction happens or not, that will have to do with the kinetics of that reaction. So here, what are favorable reactions? Well, basically, when you clash molecules together, you want the final product to be at a very low energy state. So the less the energy that product has, the more favorable the reaction to attain that product. Okay. So as a rule of thumb, the favorable reactions usually are going to release heat, and the organized byproducts are more stable than what you started with. Okay. So now, how is it that you're going to get a reaction to happen? Well, you are going to push the molecules in a certain configuration with a certain I'll say, probability of them hitting each other just right, so then the reaction can take place. So of course, we're talking here about the activation energy. Okay. So here you have your reactants, and here you have your products. But then your activation energy, if you have to put a lot of energy into that, most likely you're not going to get to the products. But you're going to see here what happens to this initial input of energy in order for your reaction to happen. Okay. So now we also have to keep in mind what is it you start with and what is it that you end up with. So when you look at the covalent bonds in your molecules, you know that you have a certain amount of energy stored there. Okay. So how is it that you're going to use the energy? Well, we could like light a match and make the whole thing burn, and then you get all the energy like really, really quickly, right? That's like, blowing up your reaction or burning the reaction. Yeah, you're gonna get the energy, you're gonna have the byproducts, they're going to be very much oxidized, right? The problem is that wouldn't be compatible with life. Another example here is the example of this chicken that is at a certain height. So this height is representing the potential energy. right? So let's say that somebody goes there and pushes the chicken out of the second floor. Let's assume also the chicken cannot fly. Okay. So you push the chicken out of the second floor, the chicken goes in here and it smashes on the floor and it dies. That's blood. Yeah. Okay. So the chicken was smashed on the floor, it will die. And yeah, the impact is the conversion of potential energy to kinetic energy, and the poor chicken couldn't keep itself together and survive. All right, so the difference from start to end is the same as if you encourage the chicken to take a step at a time and then get to the ground level intact and still alive. But then the delta G would be the same as if you just push the chicken from the second floor. All right. So again, this should be just a review of these types of concepts of energy exchange between potential and kinetic energy. Okay. So of course, if you take little steps, you are more you have a higher probability of keeping this system in a good shape, in the system intact, and you don't just burn up the chicken or the system. Okay. Now, every time you take a step in these chemical reactions, you're able to harvest some of the spontaneous heat that comes out of the reaction. If you're able to harvest a little bit of this in other energy compartments, like in other covalent bonds, then you can still keep your system at a useful state. The amount of energy that you can harvest from each of those reactions is really, really small. It's like about 5%. Okay. But it's useful because if you count all the tiny little energies that you are harvesting from each of those tiny reactions, you can end up with a lot of stored energy. Okay. So what is it that is going to control this stepwise process? Of course, those are going to be your enzymes, right? So what do you want to see here? We want to see what you start with, and you want to see what you finish with. Then you're going to calculate the delta G of that system. You're going to see, is it spontaneous um, or is it not spontaneous? Do you need to add energy in order for this thing to work? Or can you just leave it, to work on its own? So you have to be able to calculate whether something is going to happen or not based on the pathway of those reactions. Okay. So here, the question, what is it that enzymes are doing? Okay. So enzymes are not putting energy in the system. Okay. They are not going to increase the motion of those molecules. They're not going to make them, increase the temperature, make them move faster. Okay. Instead, what they're going to do, they are going to put the molecules in a certain position to increase the probability that those molecules are going to interact just right. Okay, so by placing the molecules in a certain position, those enzymes are going to lower the input of energy or lower the activation energy for the reaction to happen. Okay, so enzymes are not going to make things hotter, they're just going to make things just right. Okay. Okay, so in proper orientation. And at the same time, of course, you have a chain of reactions that are going to stabilize intermediates. So your intermediates don't go reacting with something else that is close by. So everything has to be very calculated and controlled. Okay. So that means that your enzymes are basically going to work when you want them to work. So this is the idea that enzymes are going to work on demand. We're going to see more of that concept in a little while. All right, so what is happening with the enzymes here? They are lowering your activation energy by placing the molecules in the right conformation, okay? And the enzymes are also going to allow coupling of reactions. This is a very important concept, all right? So this might be a little bit new for you if you did not take biochemistry, okay? So coupling of unfavorable reactions. So let's see what happens. What is the meaning of that? here is an example. Okay, if you have a reaction that is going from reactants to products, and your delta G is positive, meaning the reaction is not favorable, and then you use an enzyme to couple this unfavorable reaction with something that is really favorable, okay, you put them in the same space, then the overall reaction will be possible, okay? So you have to calculate whether you have enough energy with your favorable reaction, whether you have enough energy here to compensate for the amount of energy that you have to input for your unfavorable reaction to take place. Okay, so that is going to be very crucial work for your enzymes. Everybody clear with that? I hope so, although I cannot see the back of your heads. All right, so that is the principle of Hess law. Okay, so it's Hess. Kind of sounds like the Hess, right? Hess law. So that is telling you that the total enthalpy change, remember enthalpy is the stuff that is in the bonds, okay? The total enthalpy change of something is happening in reactions that are in series, one after another, okay, in series. Then you have to see what is happening at the beginning compared to what is happening at the end, and then you sum up everything that is in between, okay? So you get the energy from the beginning, well, it's all easier when you just put it in the equation. So here is an equation for you, okay? So what is happening here? You have to get the steps of every single reaction that is happening in the pathway. You need to have an idea of whether the reaction is spontaneous or not, and whether your input of energy is going to compensate for the non-spontaneous reaction. Okay, so what is happening here? If you only look at this single reaction of two sugar molecules, so this is glucose and fructose. If you get these two sugar molecules and you want to make a covalent bond between them, so here you want to make sucrose, just by putting these two molecules together, you're not going to get the bond because the input is very high. So this is an unfavorable reaction. So what's going to happen here? In this scenario, your reaction is not going to happen. Okay. So what do you do here? Well, what you can do is you can use a high energy molecule. So this is your energy currency of the cell, right? So here's a molecule of ATP. And you can use breakage of the highly unstable bond between the second and the third phosphates of ATP. So if you hydrolyze that bond, if you break that bond, you're going to get a lot of energy out of it. You're going to get, look at this, 30.5 kilojoules per mole. So this is highly favorable. You get a lot of energy by just putting water in that, using an enzyme to put water in that bond and dissociate that bond, right? And what's going to do that? Are you going to have spontaneous hydrolysis of ATP? Does spontaneous hydrolysis of ATP happen in the aqueous environment? Okay, let's go for a whole vote. How many people think yes? No, all right. How many people think no? All right, people, how many people are thinking? Yay, we got one person thinking. All right, I got everybody to think. What did I just ask? Can anybody translate to me what I asked? I can almost hear the cricket. You can probably hear the dog barking here in the background. All right, the question was the following. If you get a bunch of ATP, drop it in water, are you going to get heat out of that? Do you have a spontaneous hydrolysis of ATP molecule? Now, how many people think yes? How many people think no? All right, one person thinks no. Okay, somebody's awake. Well, the answer is no. You're not supposed to. I mean, imagine if that would happen inside of your cells. You have a lot of ATP in your cells. If water spontaneously would break that bond, uh, maybe you would go through spontaneous combustion. I don't think so, right? So you don't do that without an enzyme. You need an enzyme for that, okay? That breakage of bond does not happen spontaneously, right? Even to make that bond, right? Of course, to make that bond, it doesn't happen spontaneously. You need a lot of potential energy. All right, so here you have an enzyme, you break that bond. Now, what's going to happen? Look what is happening here. First thing that you need to do, you have a molecule that you need to activate. You need to make that molecule reactant. You need to make it more reactive, right? So by using ATP and an enzyme, I'll just put an enzyme here in the middle, you can transfer a high energy phosphate group to that molecule that was basically non-reactive. By transferring this, you're activating your molecule, okay? So you're using your energy of ATP hydrolysis to activate your molecule. Now you get your highly active molecule and you put it together with a molecule that doesn't have to be activated. But now, if you get another enzyme right here, another enzyme that gets these two molecules just right, you will be able to form this more stable carbon bond. Okay, you'll be able to make that bond and you'll be able to liberate the molecule of phosphate. So you're, deactivating that active glucose phosphate. An overall picture from beginning to end, you're going to say, although my direct path was not favorable, if you couple these two reactions, you end up with a favorable negative delta G. Okay, so coupling of reactions that is possible with enzymes will give you a favorable overall delta G. Important concept to have in mind. Oh, I didn't get the question that I usually get for these types of equations, which was like, is that going to be on the test? Right? I mean, everybody should be asking if this kind of thing will be on the test. Well, the answer is yes. Okay, so make sure you understand the concept, his law. Okay? Add up all the individual delta G's to make sure to predict whether the overall path is favorable or not. Okay. All right, so here looking more into biochemical reactions, okay? What do you need to know here? What are features of these biochemical reactions? Well, first of all, you have to check if they are spontaneous. Then you have to look at how spontaneous they are, if they have equilibrium constant between products and reactants. So this is a common feature of most biochemical reactions. They always have this equilibrium constant of association and dissociation, okay? But then you have to see how probable also the reaction is going to happen based on, of course, how fast they happen. So here, of course, you're always going to have some enzyme that is going to push the reaction one way or another, okay? And one trick that cells use, that biochemical reactions use in order to make reactions even more favorable, besides using enzymes, one trick is based on Le Chatelier's principle. So how many people remember about Le Chatelier? The Chatelier's principle. You thought you'd never hear about it again. Okay, hands up. You gotta vote, people. You gotta wake up. How many people heard of Le Chatelier? Yes, all right, thank goodness, everybody. Okay, so what's happening here? Le Chatelier principle is telling you something like this. If you have a reaction that is in equilibrium, and let's say that you sequester the product, meaning you take it away from that reaction. So your reaction in this case here is going to go to the right because you took the products away. If you have an equilibrium constant over there, well, there's nothing to equilibrate if the products are taken away. So reaction will be pushed to the right. On the other hand, if you take away the one of these reactants here, okay, if you take that one away, in that case, your reaction is going to go to the left. Okay, of course, don't take both of them at once, otherwise you have nothing to react with or go forward or backwards. Okay, one or the other at a time. So biochemical reactions or pathways, they make use of Le Chatelier's principle in order to give directionality to the overall reaction. Okay, so let's say here, for example, in this buffering system, right, of bicarbonate buffering system, if you're constantly taking away the carbon dioxide, for example, like you're breathing it out, right, you're putting it in the atmosphere, so you are also pushing your reaction to the right, okay? So you are getting bicarbonate that is at a high concentration and you're pushing it into carbon dioxide and water. You are, exhaling carbon dioxide and also water. So your reaction can carry a cellular byproduct of respiration. It can carry it away from your blood. Okay, so biochemical pathways are always going to use, or most of the time are going to use this principle of Le Chatelier. What is it that you want to sequester? What is it that what is the direction of the reaction that you want to have? Okay. So here, again, coming to this idea of equilibrium in chemical reactions. Sorry, there's some crazy dogs everywhere here. All right. So the idea of equilibrium. What is the equilibrium that we're talking about? Well, we're talking about the shift between substrate and products, okay, or reactants and products. And the equilibrium constant is going to tell you what is the tendency of the reaction, what is going to happen to the reaction. So what is the equilibrium constant? Is the concentration of products over the concentration of the substrate, right, in equilibrium. So very, very brief review. Now look at this. Of course, there is a relationship between Gibbs free energy, right, and the equilibrium constant. And this is that old chemistry equation that everybody should be familiar with. And this is telling you that how you calculate whether something is going to happen or not. Well, you have to look at the constant. You have to look at the temperature of the overall reaction. And you have to look at the concentration of products over reactants. Okay? So make sure you understand this equation. Am I going to ask you about these equations and give you calculations on that in the test? No, this is not a chemistry class, but you have to have an idea of where these numbers are coming from. But you have to know about delta G, okay, and overall reactions. Okay. So here is that idea showing you that ATP is the most used activator of molecules, right? So ATP has a very favorable delta G, which is right here, okay? Breaking that third bond right there. It gives you a lot of energy. And then the opposite happens when you want to put the bond back together. You have to use a lot of energy to make the molecule of ATP back from ADP and phosphate, right? And where is that energy? What is that energy going to be coupled with in order to get your ATP molecule back? Anybody remember that? Electromotive force inside the mitochondria, mainly. Okay, electromotive force. There are other ways of making ATP, but we mainly rely on the mitochondria. So here, comparison with the different amounts of energy that are stored in the phosphate bonds of ATP. This one here is the most energetic one. This one here is the second most energetic one, right? And the third phosphate usually is not useful for harvesting energy. Okay? Right. So here I had just shown you how ATP can activate molecules. So the activation step that is coupled with the other step for obtaining your product. Again, keep in mind that this is always happening in aqueous environment, and you're always going to be using hydrolysis or condensation reactions. All right. Now, is ATP the only high energy molecule that you have in the system? Well, of course not. It's just the most abundant one, right? Where else can you store energy, and what else can give you this push, this energetic push? Well, let's see here in comparison with these other high energy molecules. Okay, so when you look at a molecule of ATP, the high energy group that you're going to use is, of course, phosphate. Now, these other molecules that are also high energy, including you also have molecules that have even more energy than ATP. Okay, but let's look here. When you look at these other molecules here, which are also nucleotides. Okay, what they are doing, they're not using phosphates to carry energy. They're going to use electrons. Okay? They're going to use electrons and hydrogens to carry their energy. Okay. When you look at this other molecule here, like acetyl-CoA, which is also a nucleotide, the high energy group is acetyl group, and so on and so forth. So you do have other high energy groups that can donate energy from their covalent bonds in order to make reactions to happen. Okay, but one that is the most useful, the most used, the most abundant is, of course, ATP. And get ready because you have another question coming up. All right. Talking about your biological catalysts. So that is, of course, your enzyme, right? So most enzymes are composed of what? Let's start that one, please, Belle. Okay, do we have the votes in?
I can't answer this question, like it just says no responsibility.
Okay.
Like my updated stayed on 2, and then I clicked the back arrow, I clicked 3, and now it shows this.
Okay, can you take a screenshot and send it to me, please? Thank you. Okay, time's up.
Okay, so obviously, what is your answer? D, right? So most of your biological catalysts are proteins. All right, so finally, we're getting into proteins. And in the beginning of this chapter, again, there are some principles that you might not have heard of before, but they all should make sense because we're going to look at the structure, atomic structure, and organization of proteins at different levels. So first thing you should ask is, what is a protein? Is a long chain of building blocks that are amino acids. Well, how big? Well, it depends. You can have tiny proteins like dipeptides, polypeptides, less than 8 or so amino acids, or you can have these big chains that can be up to 500 amino acids. So most proteins are between 250 and 500 amino acids. And then you can have some huge proteins that are going to be like 10,000 amino acids long or so. Okay. How is it you're going to put those units together? You're going to make covalent bonds. The covalent bonds that put amino acids together, that is a peptide bond. And of course, that is a favorite because you absolutely have to know that. Okay. How many building blocks do you have? Well, for our purposes of human cells, we have 20. Are there more than 20 amino acids? Yes, but we tend not to work with them. So we're going to focus on 20 amino acids. Okay. All right, so how is it the proteins are made? Well, proteins are not just a long chain. They are going to make some blob. They're going to get some 3D structure, and they are going to have some interactions between the chain that is making this structure and other structures that will get together and maybe make this bigger blob of stuff. Okay? And we're going to see more of this in a little while. Okay. So how is it that the protein is going to be made? As we're going to be seeing, we're going to have, first of all, you're going to have to get the code for the protein that is going to come from the DNA. So DNA is going to give you the code. It's going to transcribe it to RNA. RNA is going to come out of the nucleus. It's going to go to the cytoplasm, and it's going to translate that code into those proteins. When you start to put amino acid together, amino acid after amino acids at the ribosome, the protein is going to start folding on its own just because it is in an aqueous environment. That is the cytosol. Okay, so protein is going to start fold on its own. You don't have to input energy in order for this protein to fold. Okay, it has spontaneous folding. How is it that the protein is going to fold? Well, all those amino acids in that little chain, in that little ball, they are going to make those peptide bonds, and they are going to fold in a way that is going to give you the lowest possible arrangement for all of those amino acids. Okay, so spontaneous is going to fold into this lowest possible arrangement of molecules. Okay. So how is it that the protein is going to fold, and what are the forces that are pushing this protein to naturally fold? Well, you're going to have, first of all, you're going to have the force that holds the two amino acids together. That's your peptide bond. And then you're going to have those non-covalent interactions. You're going to have those electrostatic interactions. There are hydrogen bonds, the van der Waals interactions, and even some ionic bonds, but that's a little bit tricky, okay? Because ionic bonds are not going to happen if you have the protein facing the water. Because remember, ionic bonds dissociate in the water. So the only time that you're going to see ionic bonds forming is if your protein, let's put here, a beautifully folded. So this is beautifully. Okay, so let's see here. In the inside of this protein, you have some charges. Okay, so you have like negative charge here, positive charge there. My negative charge just disappeared. Negative charge there, protein charge, positive charge here, and something like that. So if you are in an environment that is hydrophobic, so it's sequestering those charges inside these blobs and not water inside that blob, this is where you're going to have your ionic bond interaction. Okay? Make sure you understand that when ionic bonds are going to form. Okay? You have to have a hydrophobic environment for those ionic bonds to form. Remember, that's just electrostatic interaction, right? It's not real bond here. Does that sound like a good test question? Let me see heads nodding. Yes? Okay, I'll assume everybody's head nodded. All right. All right. So besides your electrostatic interaction, you also have those hydrophobic interactions. Remember that hydrophobic interactions are kind of like secondary type of interactions, right? It's not like the hydrophobic groups are really wanting to interact with each other. It's that they are being pushed because all around them there is water, and they don't like to interact with the water. So the water is pushing those hydrophobic parts to end up in one place. All right, so hydrophobic interactions are important for folding the molecule. And then besides all that, you're also going to have possibility of covalent bonds. They're going to hold this three-dimension structure together. And those covalent bonds are going to be only from a certain amino acid that is in one part of the molecule to another amino acid that is the same amino acid in another part of the molecule. And that amino acid is your cysteine. Okay? So if you have cysteine in one part, cysteine in another part, you can form a covalent bond between the two sulfurs of cysteine. So that is your disulfide bond. Okay? All right. So here, looking at levels of structure, yeah? Okay. So levels of structure of your proteins. You're going to have your primary structure. What is going to determine your primary structure is only the sequence of the amino acids that you have in that polypeptide chain. Okay? Primary structure, this is it. Amino acid sequence. That's your primary structure. There's no folding of anything. Secondary structure is going to start giving you a two-dimensional shape. Okay, so that's going to take in consideration what is happening with your primary structure and how it is folding spontaneously, but only in a two-dimensional form, because what is going to determine the shape of the secondary structure is going to be hydrogen bonds between those residues or individual amino acids in your polypeptide chain. Your following level of structure is, of course, your tertiary structure, and that's when you start to get the blobs. Okay, so following here this from secondary structure, you're gonna have this blob formation. That's gonna be your tertiary structure. And then when you compare it with a quaternary structure, you're going to get more of the same blobs that are going to start interacting with each other. But basically, tertiary and quaternary structure, okay, this level and that level, they have the same types of interactions you consider in 3D. So in tertiary structure, another test question here. Okay, in tertiary structure, you are going to take in consideration one polypeptide chain that folds itself. Okay, in quaternary structure, you're going to take in consideration two or more chains that are interacting to make that final blob. Okay, individual chains. Tertiary, one chain; quaternary, two or more. So here is just a brief overview of how complex proteins really are. Okay, if you look at other polymers that make up, structures of cells, you will see here, for example, all right, so here we have proteins. You have lipids that can make polymers. Now, lipids are looking quite simple over there, okay? You have sugars. Well, sugars can get quite complex, but usually they have repeating units, and they follow a certain pattern of repeating units. There's a polymer of sugar. And then you have like nucleotides, so DNA, RNA molecules, that they are very much predictable. Well, DNA is even more predictable than RNA because, well, RNA, if you look at 3D structures of RNA, some of them kind of look more like proteins, which is an important point to bring to class because some RNA, they actually like to behave like they are proteins. They will act like proteins, like they can be catalysts, right? Can you give me an example of RNA that thinks it's a protein? What comes to your mind? RNA with catalytic properties.
Someone said RNA viruses.
No, but I'm glad that you spoke up. That means you're thinking, yay, but no. One piece of RNA, one blob of RNA that is behaving like a catalyst, that is a catalyst actually.
Someone said rRNA.
Yes, ribosomal RNA. They are catalysts. And guess what their ribosomal RNAs do? What are they catalyzing? One brave soul. Cricket. Take a guess.
Someone said amino acids.
Very close to it. Use amino acids to make two amino acids put together. You use what?
Peptide bonds.
Yes, a peptide bond. Isn't that cool? So a ribosomal RNA is going to catalyze the formation of peptide bonds. That's pretty neat stuff. Okay, but anyway, this slide is showing you how complex structures of proteins can get. Okay, so what are the importance of proteins? Well, you can have basically everything that's happening in the body that is dependent on protein. You have structural proteins like, hair and skin, and proteins that are also participating in tendons and ligaments and bone formation, right? You have hormones or messenger proteins. You have carrier proteins. You have carry oxygen, carbon dioxide. Okay, oxygen carriers, hormones, enzymes, proteins that are serving to allow it to move, so muscular contractions. You have some other proteins that are associated with the DNA, also with RNA. You have other ones that are antibodies, right, or anti-tumor proteins. And you have some proteins that are really cool neurotransmitters, right? Even you have some amino acids that are called neurotransmitters. Okay, so important for every single thing that is happening in the body. Okay, so here, going into more details on what is happening with the formation of proteins. Here is the very, very important peptide bond formation. How do you get a peptide bond? Well, you get one amino acid and you get another amino acid. You put them together by dehydration reaction, right? Dehydration, take out the water molecule, and then you end up with your peptide bond. Okay. So you put several amino acids together and you end up with a polypeptide. Now, how do we write that in by convention? The start of your polypeptide is going to be your amino terminus. The end of your polypeptide is going to be your carboxylic acid terminus, okay, your carboxyl terminus. Okay. Between each amino acid, you're going to find those peptide bonds. Now you have to know more about those peptide bonds. Okay, so let's see what is happening here. Properties of amino acids. Those are your building blocks, right? When you look at your amino acid, you have one carbon that is not showing here, but is right there in the middle. Okay, that's your chiral carbon. Chiral carbon right there in the middle. Why is it chiral? Well, because it is connected to four different groups. Okay, so in one side you have your amino group, on the other side you have your carboxyl group, on a third side here you have a hydrogen, and then you have your side chain. Okay, when you dump this amino acid in water, okay, in physiological condition, aqueous environment, the carboxyl group is going to have a negative charge. Your amino group is going to have a positive charge. So that you call a zwitterion. It has a positive and a negative charge. That is your zwitterion. Okay. Now, when you look at the carbon that is chiral, you call that your alpha carbon. Chirality has to do with stereochemistry. Okay? That means alpha carbons will have mirror images. Now, if you look back into your organic chemistry, you remember that you can have either levorotatory or dextrorotatory types of stereochemistry. Okay, but we're going to make this really, really simple. What do you need to know? amino acids that are important for biological processes are all L amino acids. Okay? What is a L amino acid? Look at this guy over here. Chiral carbon in the center. To the left, by convention, you have your amino group. To the right, you have your carboxylic acid, just like when you write on a polypeptide chain, okay? To the top, you're gonna have your hydrogen, top facing you, okay? And then your side group is gonna be facing you at the bottom, okay? So look at the conformation of this 3D structure. That is your L conformation. D conformation, you flip the hydrogen, the carboxylic and the nitrogenous group, but we don't have D amino acids usually. Okay, so L amino acids are important for cell function. Okay, again, just to reiterate here that you have 20 different amino acids. When you dump amino acids in aqueous environment, they're going to be sweeter ions, okay? And that is interesting because your aqueous environment has to be controlled, okay? The pH of your aqueous environment is going to influence whether your sweeter ion is going to be charged or not, whether it's going to be a sweeter ion or not, okay? So here I have a couple of slides talking about the chirality of amino acids. Okay, so we say on Earth, you all find L amino acids, and that is indicative of some type of enzymatic process. And that is also indicative that we all came from the same ancestor. They're also indicative of evolution, right? So with that in mind, scientists are always looking for evidence of life in other planets, of course. Well, I find it kind of ironic because a lot of times we can't even deal with life in this planet, but you know, some people like to look for life in other planets. Okay. I would say it's more useful just to fix up what's wrong with this planet. But anyway, so let's say that some scientists are always looking for some meteorites that hit the Earth. You know, so it hits the Earth and then they run over there and they open up the meteorite and they're going to look for evidence of any amino acid in that rock. Okay. What do you think that they are expected to find? Well, they are looking, is it possible that amino acids will be present and what chirality are they? Because if they are all in L chirality or D chirality, then there is indication that there is life in other places, okay? So here, just to make this idea short here, what they found was that the L amino acid is always present in meteorites. So this would tell them that most likely there are enzymatic processes in other places, like other than Earth, that are showing formation of L amino acids. But then scientists are very strange creatures, because after they found out this information around 2017 here, they came up with the idea saying that, oh, no, this is not indicative of life in other planets. This is indicative that maybe whatever radiation is happening in space, like radiation coming from the sun, for example, is influencing the formation of those amino acids spontaneously, so there is no life in other planets. And now you should be saying like, what? Right? If they're looking for the amino acids in the meteorites in the first place to prove that there is enzymatic processes happening in other places, why are they disproving that that's the case? Anyway, forget about that. But just keep in mind that that kind of stuff is like, you scratch your head because try to understand scientists, strange creatures. All right. So again, looking here at your amino acid, what do you need to know? You need to know where is your alpha carbon, where is your amino group, carboxyl group, and you need to know it is a sweeter ion. And then you're going to start with those differentiating characteristics of different amino acids, right? You're going to have some that are acidic. Remember, acidic stuff is going to donate hydrogen, right? So if they donate the hydrogen, they'll tend to be negatively charged afterwards, after they donate the hydrogen, of course. Right. Then you have some that are going to be basic. Those are going to be positively charged. Then you have those that are not charged at all, but they have some polarity because they might have some electronegative atom in the R group, in the side group. And then you have the ones that don't have any electronegative atom in the R group, and those are the non-polar amino acids. Okay, how they abbreviated, the 3 letters or 1 letter. Okay, so let's see here what you need to know. The basic amino acids, those are going to have positive charge. Okay? Histidine is a bit of an oddball, but if you see positive charge, those are basic amino acids. What are they? Lysine, arginine, histidine. All right. Do you have to know the structures, the atomic orientation? No, this is not biochemistry class. This is cell biochem. Right? What do you need to know? You need to know lysine, histidine, and histamine. That's it. And then you have here, showing, your basic amino acids. And you say, why do I have to know the basic amino acids? Well, you need to know in what kind of environment they're going to have a positive charge. Okay. So if you look here at these 2 guys right there, lysine and arginine, the dissociation constant, look at this, is 10. That means that at pH lower than 10, they are going to have positive charges. What is the pH in your cells? pH inside of a cell, pH of the blood. What is the pH of the blood?
Someone
Anybody?
said 6.8.
Huh?
Someone said 6.8.
Hopefully not. That would mean death. pH of the blood has to be kept at 7.35 to 7.45, roughly. Very tight pH. If we go lower than 7.35, you start to become acidic. So that's acidosis. If you go above 7.45, you start to become alkaline, so alkalosis. Either one or the other side, it can become quite deadly. Okay, so pH has to be kept at a certain level all the time. Okay. Now, if this is a pK of 10, what is the charge of those amino acids in blood pH? It's going to be positive. It's going to lose that hydrogen if the pH is less than 10. Okay, so here it's telling you that's going to be positively charged. Now, if you look at this oddball here, of histidine right there, the pKa is on 6. That's quite close to the 7.35, all right? So depending on where this histidine is placed in your protein, it can exchange hydrogen or can give hydrogen or accept hydrogen temporarily, so it can have a flip of hydrogen here and there. So histidine is actually a very important residue for enzymes at their active site, okay, at the active site of enzymes, because of the pKa that is close to the pH of the environment where it is working. All right. So those are your basic. And now looking at acidic side chains, you're going to look at 2 of them, aspartic acid and glutamic acid. Okay. So aspartic acid and glutamic acid, they're going to give you, of course, aspartate and glutamate. They are going to be negatively charged at pH 7. Okay. By the way, glutamate is also by itself, it's a neurotransmitter. It's a very important, it's saltatory neurotransmitter, right? So that's your glutamate. You can add amino groups to aspartate. If you add an amino group to aspartate, you end up with asparagine. If you add an amino group to glutamate, you end up with glutamate. Right, so besides that, this okay, a couple of slides before I quit here. Uncharged amino acids that are polar. What are you looking for? You are looking for electronegative atoms in your side group. Uncharged polar amino acids. Okay? So know what those are. So asparagine, here's that one here. Glutamine, serine, threonine, tyrosine. Non-polar side chains. You are not going to find electronegative atoms in those side groups. No electronegative atoms in the side groups, except for cysteine, or the sulfur is a bit electronegative. But this other thing about amino acids, sometimes they can fall into one or another category depending on what property you are looking at. Okay, so you can argue about cysteine, but the rest of those are non-polar side chains. And some of them here, like, oh, it has a cysteine, it has a nitrogen here, but the bulkiness of the amino acid side chain is really non-polar. So here, putting them in buckets, you have here acidic, basic, and here you have your polar amino acids, and then you have your non-polar amino acids. Okay. So I am going to stop in this slide, but pay attention because I will add the conclusion of these slides for you to catch up for self-study, okay? So on Monday, we are going to cover this, and we are going to cover the rest of your amino acid story, of your peptide bond story, okay? Make sure you watch those videos. I'm going to hang around here for some more time.
Yeah.
Let me also put it here. So I put it in the recording for the class as well. Let me pull up here 1 second.
All right, thank you. Yeah, the reason why is because it's very helpful. I see that it's very helpful, and I wanted to use it for different classes
Oh
with
yeah,
different.
absolutely. Okay, so this is what I'm going to do here. I'm going to share my screen again. Okay. Okay, actually, I just found out yesterday that there is a limit of how many podcasts you can make in one day. So you have to pace yourself accordingly, or they're going to charge you a lot of money for that. Okay. All right, so here we go. You can see my screen here, right? Artificial intelligence. Okay, so what do? You go here, fau.edu/AI tools. You go down
Okay.
here. Okay, let me see the one that I can recognize here. I don't know how to use all these other stuff. Then I learned this one here. Okay, Notebook by Google.
Oh, that's what it's called? That's what it is?
Notebook LM, this guy here, Notebook LM. So you get here, you go access Notebook LM. Okay. So here you say try Notebook LM. And of course, to access the site, you have to be logged in with a FAU account. All right. So here you see I have several little notebooks that I made with these podcasts, into these podcasts. Okay. So what do? You go here and you say create a new notebook. Okay. Here you're going to upload a file, but it has to be a PDF file. Okay. So let me show you here.
Okay, I get that.
Okay, when you get here, all right, for example, this guy here. All right, this is the end of this lecture today. So I want to go here and I say, okay, sulfur-containing amino acid, and the rest of the story here for amino acids. So I will choose at the most like 10 slides, okay? So you get these 10 slides, you prepare a new PowerPoint or convert them into a PDF file, okay? Once you have your PDF file, you drop your PDF file to this add source, okay? So let me see here. I had one that I was making before. Let me see if I find it. I can show you a second.
Okay, I
So
think I got the idea of it. So I think what I'm gonna do, I'm gonna go home and play around with it and
yeah,
um
you're
see
playing
how
with
it
it.
works.
Okay, so here it is. One second, I found it. Okay, so here we go. Once you have your file there, it will automatically give you a summary. Then you go into these four little things that you can play with. You click on the audio overview,
Oh, okay, okay.
okay?
Yes.
I did not like this video overview because it's distorting whatever I put in the slides, and I didn't like that. Okay.
Which one? The video part? The second
Yeah.
one?
Yeah.
Okay.
I did not like how it
Okay.
distorted the information. Okay. So you just
So
listen to.
is that the version that you posted on YouTube, the podcast, the video version?
Yes, but as you see, I put images to it, but then I use another program. Okay. So I use Camtasia for that, but that is paid subscription. You don't need that. What you do, you just follow the PowerPoint slides and you listen to the explanation in the podcast, and that's the same thing.
Okay, got it. And um it has to be like it can't be a large file PDF. It has to be like broken up, not too big.
Yes and no. You can have a bigger file, but then AI is going to determine what it thinks is important for you to have in the podcast.
Okay, got it. It's gonna try to summarize it in some way.
Yeah, it's not going to give you more than a 15 minutes podcast.
Okay, got it. Okay, I see why
Okay.
it's important to chop it up.
Yeah,
Okay.
otherwise you're going to miss some information.
Okay. Well, thank you. I did send you an email regarding that, so if you do get to it, you can just ignore it
Oh, okay,
because you
cool.
answered my question. Thank you.
All right, you're welcome.
Bye.
Bye.
Hello, Professor.
Hi.
Hello, I had a question on one of the slides, slide 22.
Slide 22. So let me bring that one up. Okay.
Because I wanted to ask about the like the part of the energy available to drive energetically unfavorable reactions. Like it has to be less than 0.
Once this slide 22.
Yes, that one.
What this slide is telling you is that when you hydrolyze this unstable phosphate bond in ATP, you are going to liberate energy from that bond. So the delta G is less than 0. So the reaction is favorable. Okay, it's not going to happen by itself just because you put water in there, because this is a hydrolysis reaction. Okay. But if you have an enzyme, then the enzyme can allow the water molecule to break the bond for you to harvest the energy of that unstable bond. This is what this means. Okay? This energy can be used coupled to unfavorable reactions. So when you couple this energy with something that uses up energy, then you have to see, okay, how many kilojoules can I get from breaking this bond? And how many kilojoules do I need to drive the unfavorable reaction? Okay. If you can get 35 kilojoules breaking this bond, but you need 45 for your favorable reaction, so this thing is not going to happen because the overall delta G is still going to be positive. Okay. But if you get 35 from breaking this bond and you need 20 to drive your unfavorable reaction, then this thing is going to happen because overall you're going to have negative 15 kilojoules of energy available of delta G.
From the 35 to the 20, the negative 15.
Well, let me go to that example that I gave before, like this example here. Okay. So let's see here. Breaking ATP, like the first phosphate, okay, you get like 30.5 kilojoules. So this is negative delta G. It is highly favorable. Okay. If you are going to just make this bond without activating the molecule, if you're just going to make this bond, you're going to need to put energy for 23 kilojoules. So this is highly unfavorable. This is not going to happen on its own, okay? So what do you do here? You use an enzyme to couple these two reactions. So the first thing you do is you activate this molecule with ATP. So here is breaking up this ATP molecule. You're going to use some energy to make this bond, but it's a lot less than the energy that you can get out of the reaction of the phosphate bond. Then you are going to get another molecule here of fructose with your activated molecule, and you have an enzyme to make this other molecule that is also favorable type of reaction. So this reaction is favorable, that reaction is favorable. Overall, you're going to end up with sucrose and byproducts, but if you add the delta G of this reaction with the delta G of the other reaction, you're going to end up with the overall negative delta G. So putting them together gives you a favorable reaction. Okay. And this is not very accurate because it should be telling you exactly what is the energy you're getting from here, what is the energy you're getting from there. So it should be broken down in more pieces, but overall, the reaction is going to be negative delta G.
Okay, so coupling the reactions like helps make an unfavorable reaction favorable.
Yeah, if you couple your unfavorable and favorable reactions, if your delta G at the end is negative, then you make the whole thing favorable.
Okay.
Okay?
Yes, makes sense. I had another question for slide 31. Well, this was just to make sure. I wrote down that electrostatic forces, you mentioned that they're not bonds or they're not interactions.
They are interactions. They are not covalent bonds.
Oh.
They are interactions.
So that's the only one that isn't a covalent bond. The other ones are.
Well, hydrophobic interactions are also not covalent bonds, but then those can also fall into van der Waals interactions. Okay, so hydrophobic interactions and van der Waals interactions, they're kind of more or less in the same bucket, although van der Waals interactions really are looking at shift of electron cloud. Okay, but those are all electrostatic interactions. Then besides those electrostatic interactions, you also have real covalent bonds that are holding polypeptides together. Then the only time you get, besides your peptide bond, right, that's holding individual at the primary sequence, you can have disulfide bonds that can stabilize the structure of proteins. Okay, and then you're only going to get disulfide bonds if you have two cysteine residues that are in a conformation to interact.
Okay.
Okay.
And I just wanted to make sure for slide 39, what we mainly need to know is like if it's a L-amino acid, if it's like the amino group on the left and the carboxyl group on the right. And then if it's a D, it's
Yeah,
what?
that's the easiest way to remember the L amino acid. But mainly, I want you to know that there is a stereochemistry So basically, what is this stereochemistry and which amino acid is the prevalent type, which stereochemistry is found in living systems. So the L amino acid. And then it's easy to know here because you have, as by convention, amino on the left, carboxyl at the right, hydrogen at the top, and side group at the bottom. So you should be able to identify the L amino acid, but I'm not going to ask you specifically because this is more for organic chemistry type of orientation, left rotatory, dextro rotatory, that's too much.
So what do you mean by like prevalent type? Do you mean that it's like more favorable for the L amino acid?
Those are the ones that you find in living organisms, yes.
Okay.
And should it also be indicative of enzymatic process because all the amino acids have the same L configuration. So, something is happening with some enzymatic processes to make those amino acids.
Okay. Yeah, those are all my questions. And I wanted to ask, from the iClicker app, it shows up like some days are like I was like absent, but I was present to all days. Like, would that be fixed or were those days like test
So don't
off?
worry about it. The only thing is that, if you were present, do you have other points that were on that day?
I still like got the points of that day though, I think.
Oh, that's strange. And you said you were absent. That's weird. Yeah, but don't worry about that because that's, I'll give plenty of iClicker points that, you're going to have some buffer zone of extra credits that can be missed. So it's not going to affect you in any way.
Okay, because I wanted to ask because it says like possible points 8 and I only got 7, but like from all the iClickers I answered, like I got them right. So
When was that?
that it says the total possible points are 8 points, but like I've only like got 7.
Which day
But
was that today?
it doesn't show. It just
Sorry?
shows like it doesn't really show it on the thing. Because I've like obtained all the points like correct, but it doesn't mark it.
It doesn't show you which day it was?
Yeah.
That's strange. Try to see with Belle if she can figure it out. Otherwise, we can look at it once I'm, there. I'll sit with you and open the app and try to figure that out.
Okay. And to make sure for the exam I was taken online, is it through lockdown browser?
Yes.
Correct?
Oh, I forgot to mention that. Yeah, it's through Lockdown browser.
Okay. Thank you.
You're welcome.
Hi, Professor. So I have a few questions.
Mhm.
On the exam, are we going to be analyzing pictures like you have in your PowerPoints, or are they all just words?
I like to put some pictures. Yeah, you're gonna have some words, some pictures, and yeah.
And then the other thing too is, I mean, this is terrible, but I've forgotten a lot of the general chemistry stuff and a little bit of the orgo. So I noticed going through the PowerPoint that what you're saying in class verbally is adding on to information that's on the slides. So it like I'm trying to keep up with the class, but I'm not able like if I'm reading the PowerPoint on my own, I'm afraid that I'm not getting the information that you're saying in class. So when I'm studying, I feel like I'm going to miss details that should pop up. So what do I do with that?
This is also why I make the videos. So in some points, you miss a little bit here or a little bit there. You can go to the specific section of the video and review it. And another thing that you can do is use AI, when you're studying. You get one session, or you can get a couple of slides of the PowerPoint slides and dump it into Chat GPT and say, explain what is in this slide, you know, or make multiple choice questions based on this information. So this is, of course, the subject goes into a huge level of details, but I'm really trying to break it down as much as possible. But yeah, make sure you catch up with the videos and the extra material that I add.
And then the podcasts, they're doing a summary of all this, or what exactly are the podcasts doing?
Yeah, in the podcast, I was basically breaking it down by topics, and I really like the way that they put it in this like conversation type of setting, that it really makes sense and it's easy to listen to.
And then obviously, I mean, I know everyone else does, but I've been having a lot going on where I haven't been able to read the PowerPoint, so I think that's also adding to my confusion. If I were to read the PowerPoints, do you think I'd have a better handle on all this?
Yeah, take a look at the PowerPoints before you come to class. Even, of course, the PowerPoints that I have up there are still from last year, but the subject is the same. So that will give you a better understanding of what, of what we're talking about in the class. Take a look at the PowerPoints before the class. That will help a lot.
Okay, thank you.
Welcome.
Hello, Professor.
Hi.
Can you go back to the slide with where it says controlling the burn?
Controlling the burn.
The one with the chicken that you had jumping off the two-story building.
Okay.
Slide
Here's-
14.
Yeah. Okay.
Can you just go over that slide for a moment, please?
Okay. So this is showing you that you have a certain level of potential energy that is inside of the bonds. Okay, let me just say, am I recording this? I don't know. It's paused. So this might, if you're having a question with this, the people might also want to. No, I don't know what to do with this thing. A second. It's actually recording. Okay. So what is happening here is that you have a certain level of potential energy that you have in the covalent bonds in molecules. Okay. So you can either harvest all the energy at once, or you can harvest it in little steps so that you don't destroy the molecule you start with in the first place. Okay. If you harvest all the energy at once, for example, in a sugar molecule, you're going to burn the sugar, like really, you're going to burn the sugar, and the temperature is going to go way high, and that's not going to be compatible with life. Okay. So instead of just burning the sugar, if you break one bond at a time using a little bit of energy harvested from that bond, and then the next bond, and then the next bond, so that way you can save your system from total combustion, and you can use the energy that is stored in the bonds, okay, to keep the system alive, basically. Does that make more sense?
Yes, it does.
Okay. Yeah, that's the whole idea of this slide, is that let's say if you go from molecule A to molecule F in one step, you might just burn this whole thing out.
Okay, that makes more sense.
Okay, great.
And then I have one more question.
Okay.
So for the exam, in order not to like overwhelm myself for trying to make sure that I got everything, because I know I should at least try to memorize as much as I can. Do you know like what the breakup is gonna be between like each chapter? Like how much of
No,
each chapter you're gonna prioritize for the
I'd say
exam?
focus on the PowerPoints and what I explained in class, because I didn't even put the exam together yet. You focus on the PowerPoints and what I explained in the class. Because all the questions I take from what I explained in the class. And of
Okay.
course, if you self-study videos, then yeah, I'm gonna cover that because I took a lot of time to actually put those videos together. So you guys should know what is in there.
Okay. So just use all the resources that I have.
Basically, yeah, focus on the videos and the PowerPoints. Yeah.
Okay. Thank you very much.
You're welcome.
Have a good day, Professor.
Thank you. You too.
Thank you.
Okay, so I guess everybody's gone.